for Boolean circuits, the way that we're going to identify our complexity classes is going to be by the number of NAND gates that are required to implement some function. So the idea here is we're categorizing functions in our complexity classes according to the size of the smallest circuit that can implement them. So for instance, we could have a complexity class that is going to be all of the circuits that could be implemented using only the number of NAND gates that are in this bowl. So that would be any function that can be implemented using a circuit with 120 NAND gates or fewer is going to belong to the complexity class associated with 120 NAND gates. So that count of 120 NAND gates. We could have a different complexity class for all of the functions that can be implemented with circuits that use 60 or fewer NAND gates. So essentially, each of our complexity classes is going to be defined by an upper bound on the number of NAND gates that you're able to use. So in this sense, our complexity classes are sort of going to be nested, that everything that belongs into the complexity class of 30 NAND gates is also going to belong to the complexity class of 60 NAND gates, which will also belong to the complexity class of 120 NAND gates. So as an example where we've already been able to sort of demonstrate membership in some complexity classes, we proved last week that we could implement any finite function with n input bits and m output bits using c times m times 2 to the n gates or fewer. So there always exists some circuit that can compute any n input m output function using c times m times 2 to the n gates for some constant c. Now that tells us that if we look at the complexity class of all functions, the set of all functions that can be implemented in c times m times 2 to the n gates or fewer, that's going to actually contain all n input m output functions in general. Now, some functions are going to require a lot less than that bound. So for instance, when we looked at if, I think that if required something like 4 NAND gates to compute. That's way smaller than that c times m times 2 to the n threshold. So that would also belong to a smaller complexity class. So this tells us that if is sort of a less complicated function than some other functions that are going to have the same number of inputs and outputs. So hopefully you can see a little bit of how this is helpful in being able to compare the hardness of various different functions. So the notation that we're going to use in order to refer to our complexity classes for Boolean circuits is this size notation. So when we say size of S, that is actually going to be the set of all functions that can be implemented by Boolean circuits using S or fewer NAND gates. So we could say size of 120 is going to be all of the Boolean functions that can be implemented with the number of gates that are in this bool. And so this tells us that like size of maybe 10m times 2 to the n is going to contain all of the functions with n input bits and m output bits. Now when you look at the textbook, you're going to see that there's a couple of different versions of this size operator, where sometimes there's going to be subscripts that are associated with that. And that's essentially restricting the kinds of circuits we talk about. So when we say size of S and there's no subscripts at all to that, that refers to all of the circuits in general that can be implemented using S or fewer NAND gates. If you see 2 subscripts to that, so maybe size n comma m, where n and m are the subscripts, that restricts it to only the n input and m output circuits that require S or fewer NAND gates. So when we look at size sub n of S, where we just have that single subscript n, that's saying that the number of input bits is n and the number of output bits is 1. So that's all the n input, 1 output functions that can be implemented in S or fewer NAND gates. So now we had mentioned that size of 60 is going to be a subset of the size of 120, because anything that can be implemented in 60 or fewer gates can also be implemented in 120 or fewer gates. But these aren't necessarily going to be proper subsets. So it might be the case that if I had maybe 120 gates available to me and I ended up with one gate fewer, now I got 119 gates, I might not have lost any functions after all. Sometimes there can be gaps in these complexity classes where anything that could have been implemented in 120 gates, maybe there is also a way to implement it in 119 or fewer gates. So that is possible. So when our complexity measure goes up, we could get more functions. We're definitely not getting fewer functions, but we might not get any more functions after all.